Alright, and so my first question in this video is we just finished talking about coordinate curves. Why are they actually useful? Well, I'm going to tell you that they actually help us in this video when we're discussing tangent planes. They help us to describe if we're looking at a point, right, and we're looking at creating tangent vectors at that point, or the tangent plane, we can actually look at the coordinate curves to help us with that. Okay, and these tangent vectors that we use to construct the tangent plane are given through this form. So again, we're on a parametrized surface, so we have to have that. And so here, when we're looking at tangent vectors, tangent vector for the with respect to vector, or to the parameter s, is, and then we take the partial derivative with respect to our first parameter at that point. Okay, and this is where notation becomes a pain. But it's succinct. Okay, it is succinct. It's just not pretty to write out all the time. And so the idea being here that if we're looking at some surface, okay, and I'm going to draw this little surface here. Okay, we have a little curve here too, and same thing here, and then we connect it there. And what we're trying to do again is to say, okay, well, on this surface we have a point x of s naught t naught. Okay, and what we're going to be doing is looking at tangent vectors in this direction, which might be t of s at s naught t naught, s naught t naught, and then similarly we're going to look at the other direction, t of t, let me fix my notation here, t of t of s naught t naught. Okay, and I forgot a comma in there, but you get it. Okay, and so these two vectors are going to hopefully span the tangent plane. So, and then from all this we get a little tangent plane right at the point. Okay, something like that. But I'm going to undo that just so my picture doesn't become overly messy. Come on. Alright, there we go. Okay, and then with these two tangent vectors that will span the tangent plane, we can write our tangent plane in parametrized form. Woohoo! Alright, so you'll notice that we have our point, right? Okay, so this is our point. This is our first parameter, right? Okay, first parameter. And then we have our first spanning vector, okay? And then we have our second parameter, yay. And then we have our second spanning vector, okay? So, intuitively, once we get these vectors, it all makes sense because we know how to parameterize a plane. Okay, but getting them could be a little interesting because you have to do a derivative of the parameterization, or of the parameterization with respect to each variable, plug in the point, go on from there. Okay. Another form, so this is one form that we learned for a plane. The other form we learned was the normal form, right? And so we could say that it's this n vector dotted with, and then this is x minus x o, and so this was our n dotted with x times xo that we studied way back in Calc 2, and so we can use that here as well, and we call that our standard normal vector. Okay, now actually creating it, you'll notice that there is a cross product. Okay, and that makes sense because if we have two vectors that span the plane, we can take their cross product, span the tangent plane, we can take their cross product, and that'll be normal to, or so that it'll be perpendicular to both of the vectors that we use to create that span, which then is normal to the entire plane. Okay, So, great. We can go ahead and do that easily, right? Well, maybe not. Okay. So here we want to compute the tangent plane to the sphere. Okay, our parameterization that we saw before at this point. Okay. Well, this is going to be interesting. So, if I find, so I need to do this in pieces, right? Because I need to find the two tangent vectors. Okay, so if I do this, I need to differentiate. So it's, for this one, it was differentiate our parameterization with respect to the given variable. Okay, let's do that first. I got to do this one at a time. Okay, so I differentiate, and we end up getting negative sine phi sine theta, and then sine phi cosine theta, and then 0. Okay, and then I plug in, so now I need to find this at our point of interest. So pi over 4, pi over 4, okay, and what I end up getting is minus 1 over, or 1 half, and minus half, and then 0. Okay, that's fine. And then now, so that's our first vector, yay. And now I want to do this with respect to the second variable. Okay, and when I do this, I get cosine theta cosine phi, sine theta, sine theta cosine phi, and then minus sine phi. And then at our point of interest, pi over 4, pi over 4, I get 1 half, and then minus 1 over root 2. Okay, that'll be my second vector. Okay? So then the tangent plane I can write in one form as the point, so I need to find, if I put in the point, what I end up getting, so t of u and v, what I should get is 1 over 2, 1 over 2, 1 over root 2, okay, and then plus u times the first vector, 1 half, 0, plus v, and then second vector, 1 half, negative 1 over root 2, okay, and then specify that u and v are within the real numbers. Okay, I could also use the normal vector definition. Okay, and if I do that, I would have to find n. Okay, and it turns out that if I find n and plug in pi over 4, I get negative 1 over 2 root 2, negative 1 over 2 root 2, and negative 1 half for the vector, and I'm misusing notation here a little bit, I apologize, but then what I end up getting is that it would be negative 1 over 2 root 2, comma, negative 1 over 2 root 2, and then negative 1 half, dotted with, and then x minus 1 half, y minus 1 half, and then z minus 1 over root 2 is equal to 0. Okay. Either way, if the second one would work if we didn't want a parameter in our tangent plane, but this problem didn't really specify. Okay, so that kind of concludes this video, finding those tangent vectors, and then either using a parameterized version of the tangent plane or a non-parameterized version with x, y, and z. All methods we're familiar with, just now using surfaces.